Hello, my wonderful AP Statistics students. Welcome to another video in Unit 1, Exploring One Variable Data. If you're new here, I'm Goldie and I'm here to take you through our AP Statistics course. In this section of notes, we are going through comparing distributions. So we're actually going to talk about how to describe distributions and then also how we use comparison words to compare two different distributions. So we're going to be going over all of this information together today. So grab your notes, get settled in, and let's go through this content together. So first, let's talk about describing distributions because we have to know how we describe them before we talk about actually comparing them. So first, let's talk about shape, okay? And in order to talk about shape, we have to see kind of where we're going with how we describe distributions. We talk about shape, outliers, center, and spread. So we're going to talk about shape first, but we're eventually going to talk about all four of these things. Whenever you're asked to describe a distribution in AP Statistics, you want to comment on these four main things. Now, we don't describe categorical distributions this way. We only do it with quantitative data. Why don't we do it with categorical data? Well, remember, you can't find the center and spread of a categorical variable, and shape doesn't matter in a categorical variable graph because you can put the data in any order you want. So when we're looking at these examples here in a moment, we are only talking about quantitative data. Okay, so keep that in mind. Now shape. Okay, once the distribution is graphed in whatever way you end up graphing it, the first thing we notice is the shape of the graph. And we always say graphs are a great way to visualize data. And one of the ways we visualize it is by describing the shape of it. Okay, so here's the first way we describe it. We can describe it as unimodal. Okay, so unimodal would be a graph that has a peak somewhere in it. Like in this histogram example, we have a single peak. So if I were to draw, you'll see me quite often kind of draw like a smooth line. Ooh, I used red. Look at that. You'll see me kind of draw like a smooth line over top of graphs. That's just try to give you a good visual for the shape. So here, this would be one peak, and we call that unimodal. Bimodal will be two peaks, right? So if we kind of draw a visual here, we have two peaks somewhere in our data. Okay, not necessarily, they could be at different levels, right? This example, they're at the same level, but maybe different levels, but there's still two peaks somewhere in our data. We call that bimodal. Another description of shape we use is uniform, and it's where data has approximately the same values across. Again, in this example, I give you the same value across, but maybe it might look like something like that. Like it doesn't have to be exactly the same in order to be called uniform, but approximately the same value across. Okay, isn't that a beautiful graph? Yeah, I was an artist in a separate life. Okay, symmetric. Another way we use to describe graphs. Symmetric is if we split the x-axis in half, we get a mirror image. So if we were to like fold our graph up across the x-axis, we would get a mirror image. And again, we can describe something as symmetric or approximately symmetric. It doesn't have to be perfect. Nothing is quite perfect when dealing with data. But we would use to describe something like this to be symmetric. Or even if it looks something like this, approximately symmetric, something a little bit more bell-shaped, we would describe that as symmetric. A lot of different graphs we would use to describe something as symmetric. The other way is skewed. Okay? Now, skewed graphs, there's two types of skewed graphs. The first one is left skewed. And a left skewed graph means the tail of the data is on the left of the x-axis. Okay? Now, this is a little crude, but for some reason, whenever I describe it this way, students remember it. Okay, we talk about the tail of the data, right? So here we have like a tail because it's kind of like a small little piece hanging off. Like if you think of a dog, right? They have a tail hanging off. If you grab, what hand do you grab the tail with? That's how we describe it. So I grab this data with my left hand. So I would grab, like if you grab a puppy dog tail, right? What hand do you grab the tail with and pull? Well, don't pull the puppy dog tail. But if you were visually grabbing a tail, what hand do you grab it with? That's how you can remember left skewed and right skewed. And I'm sorry I have the image of pulling puppy dog tails in your head, but I don't know, it helps remember. Okay, so pull the tail. This one, I would grab it, if I'm looking at the graph, I would grab it with my left hand and pull with my left. The tail has less data, and left skewed means that there's more data on the right. Okay. The opposite is true with right skewed. Right skewed, the tail is on the right of the x-axis. So we grab the tail with my right hand, and it would be right skewed data. Less data on the right, more data on the left. Okay, little puppy dog tails. Okay, now when we are asked to describe shapes of a graph, usually we use a combination of those shape names. Okay, and here is some examples of what those look like across various graph forms. Now, if you're taking your notes, you can just draw an approximate shape of each graph. Don't worry about copying this graph down exactly as I have it written. You can just kind of use lines to summarize. You don't have to write down the exact data values. I just want you to write down a visual that's going to help you, okay? So here are the three main shapes. Of course, we have a dot plot as well. And a dot plot, a dot plot is very similar to like a histogram or a stem plot, so I didn't include that example. We have also talked about cumulative relative frequency graphs, or ogives. They don't really follow this in terms of shapes, okay? So we don't describe an ogive with shapes. And then, like I said, categorical data in that graph we've discussed isn't described with the shape. So here's what we would do. If I were to call a distribution symmetric and uniform, what that's going to look like is something like this on a histogram, something like this on a stem plot, and something like this on a box plot. Okay? Histogram and stem plot, they're very visual. So if something's uniform, you can kind of pick it out right away. Box plots are going to be a little bit different when it comes to shapes. They're a little bit newer for you guys, and you're going to have to kind of get used to them a little bit. But a uniform distribution, the box and whiskers are similar in length. So for a uniform distribution, the whisker is approximately the same as each quarter. So each quarter is the same, right? And similar in length in some way. Okay, and symmetric would be the median in the middle. Okay, and then symmetric on either side out to the min and max. Okay, so this would be a symmetric uniform. Symmetric bimodal. Okay, a histogram, again, easy to see, has that bimodal shape. Stem plot, you'll have to kind of visualize as it's almost like a histogram laying on its side. It got tired. And you can see the bimodal shape there. This would be like your x-axis. So if you just turn it on its x-axis, that's how we would describe that stem plot shape. Now, box plot is a little different. Here's a box plot of this exact same symmetric bimodal data that's in the histogram and stem plot. And you can see that it looks very similar to a symmetric uniform. And that's because it's hard to see bimodal on a box plot. Okay? It is very hard to see bimodal on a box plot, but it is there. Okay? It is there. It's just the way it's split up. It's hard to see that's the shape. You can see the symmetric shape because the median is in the middle. So you see the symmetry in there. It's easy to see symmetry, but it's not so easy to see the difference between unimodal and bimodal on a box plot. Let's talk about left skewed. Unimodal, left skewed. On a histogram, you're grabbing the left tail of the histogram. On a stem plot, again, turn it, if this is the x-axis, turn it on the x-axis, and you can see the tail is on the left side, and this is the right side, okay? Sometimes it might dip off a little bit. Sometimes it doesn't dip off a little bit. But the majority of the data is on the right side. Majority of the data is on the right side. Okay. For a box plot, what that looks like is a longer left whisker. Okay. So when we talk about left skewed, grabbing the tail, on a box plot, you're going to have a longer left whisker. So heaven forbid you go up to a cat and you grab its left whisker, right? Left whisker means left skewed. Okay, if there's a longer left whisker, we are left skewed. Okay. That doesn't bring me as much sorrow as grabbing a dog's tail because I'm not a cat person. I hate to say it, I'm not a cat person. So grabbing a whisker doesn't make me as sad as grabbing a puppy tail. No, don't hurt animals. Don't hurt animals. Unimodal right skewed. On a histogram, here's a different shape. We have the unimodal right skewed here. Again, majority of the data is on the left and the tail is on the right. So a stem plot, what this would look like, something like this. Majority of the data is on the left now, tail is on the right. And a box plot, you have a longer right whisker now, okay? And you'll notice that it's not quite so symmetric, okay? Because it has a longer right side and a shorter left side, okay? And here, if something does not fit any of the main shapes we've discussed, we call it multimodal. Okay, so something like this, right? If you were to give me this, I'd be like, what the hey is this? How do I describe something like this? Just call it multimodal. Okay, here's a stem plot of it, just something strange happening, right? Again, easy to see it's not symmetric, hard to see other patterns when it comes to a box plot. Okay, so I can see, okay, I'm not symmetric over here. But what else is going on, right? It almost looks like, okay, maybe it's left skewed. I don't know, because there's majority of the data over here. But it's hard to determine that shape from a box plot specifically. Okay. All right, so that's all about shape. Okay, we got 3 more: outliers, center, and spread. Okay. Now, outliers. When we're looking at a graph specifically, we want to comment on any visual outliers, okay? So like in a histogram or in a box plot, it's that one data point that stands out, okay? Anything visually outlier. Now, of course, we have the 1.5 times the IQR and the 2 times standard deviation, both rules to mathematically determine outliers. But if you were just to look at a graph and asked to describe the distribution, you don't necessarily have to do the math to find outliers, okay, if that makes sense. You can just comment on the visual outliers saying, yes, there's a visual outlier, or no, there's no visual outliers. Center. So when deciding what measure of center to use, it's best to consider the shape, okay, and if it has extreme values, because we know extreme values and outliers affect certain measures of center differently. So remember, the mean is non-resistant. So it's best to use the mean when you have symmetric and non-skewed distributions. You can use it in a bimodal or a unimodal distribution, but if you have no extreme values and everything looks pretty symmetric, use the mean. The median is resistant to extreme values. So when you have skewed distributions, or you have extreme values that you are keeping in your distribution, it's best to use the median. Okay. In a skewed distribution, and remember, skewed distribution doesn't mean you have outliers. Okay, a skewed distribution just means you have a longer tail of data, but not necessarily that those data values are outliers in any way. We just call those more extreme values. Okay. Now the median is a better indicator of center in a skewed distribution because the mean always gets pulled towards the tail. And here's a visual of that. So in a unimodal symmetric distribution, the mean is approximately equal to the median, which is approximately equal to the mode, right? Pretty, beautiful. We love that, okay? Now, when we start getting skewed, however, things start getting pulled. Okay, so in a left skewed distribution, the mode is still the most occurring value. Maybe it occurs in the biggest hump there, right? The median gets pulled a little bit, but not as much as the mean gets pulled towards that tail. Okay, so in a left skewed distribution, the mean is less than the median, which is maybe approximately equal to the mode, maybe a little bit less, okay? But the mean for sure. The mean is for sure less than the median, okay? Vice versa for the right skewed. Okay, in the right skewed distribution, the mean gets pulled up towards the tail, so the mean is higher than the median in a right skewed distribution. Okay, that is something you do want to know. Okay, that means because if you know what your mean and median values are, if your mean and median are approximately the same, you know, okay, I'm dealing with a symmetric distribution. Okay. If your mean is much smaller than your median, then you know you're dealing with a left skew distribution. If your mean is much higher than your median, you know you're dealing with a right skew distribution. So knowing these values, you can start to picture the shape of your distribution. Okay. Okay, the last thing is spread. And we have different ways to describe spread. If you have data and you use mean as your measure of center, you can find the standard deviation. Okay. If you have data and use the median as your measure of center, you want to find the IQR. If you don't have any data, just report the range from the graph. Okay. So the mean is used with standard deviation and the median is used with IQR. That is very important. Those go hand in hand. You don't want to mix those up. Okay. But remember, we choose the mean or the median based on the shape. And once you have the center chosen, that leads you to describe your spread. Now, standard deviation and IQR, they are very difficult to determine from the graph itself. You would need data to determine their exact values, which is why if you don't have data and you're asked to describe the spread, the range is the better option because you do get an approximate range from the graph. Okay. Again, not an exact range, but you do get an approximate range. Okay. So here, describe the distribution below by commenting on the shape, center, and spread and potential outliers. So this is kind of more what you'll be given on the AP exam. You will be given a graph, but then you'll also be given summary statistics. Okay. And you can use that to support how you're describing your distribution. So this data is the word length for Taylor Swift's song, I Can Do It With a Broken Heart. Which is just currently on repeat in my head forever and ever. So in the graph, we have all of the word lengths put in our histogram. So we can see here, just to kind of explain the graph, right? 1 to 2 means that all the words that have a length of 1 are here. All the words that have a length of 2 are here, 3 are here, etc., etc. Okay, and their frequencies. So we start off by commenting on the shape. The distribution is right skewed. I can see that it's right skewed. It has a longer right side tail here. So I would say the distribution is right skewed with a median value of 3. Okay. Now, because it's skewed, that's why I went with the median to describe the distribution. And since I went with the median to describe the distribution, I want to report the IQR. And that value is 2. Okay. Now, you don't necessarily have to show the math that got you to those values. Okay, remember, you can just put them in there. And then we also want to comment on outliers. There's no visual outliers, but there are a few extreme values, right? So these, they still fit with the data set, okay? They still are with the data. There's no gaps in the histogram to indicate that you might be dealing with an outlier, but we do say there's a few extreme values. I don't have to go in and do the 1.5 IQR rule. You don't have to worry about that when you're describing a distribution. You just want to comment on what you see when you describe the distribution. Okay? That's describing a distribution. Now we have comparing distributions, which is what this section of notes is over, okay? Now, comparing distribution is actually doing what we just did, but doing it for 2 graphs and making sure that we're using comparison words between the 2 graphs. So I have an example here. Do students in AP classes spend more time on homework than students in non-AP classes? I had a random sample of 21 what we call AP students, or students who were enrolled in 1 or more AP classes, and 20 non-AP students that were asked how long they spent on homework last night. And the data is shown in these histograms. Okay? Time spent on homework last night for AP students and time spent on homework last night for non-AP students. Okay? So take a moment, absorb, look at those beautiful graphs, and we're going to compare them. Okay. Now let's talk about how we're going to do that first. If we're asked to compare 2 distributions, we still want to comment on those things we just talked about, shape, outlier, center, and spread. But comparing, we need comparison words and descriptions. We want to be very purposeful with that. Okay. So for example, if I said the distribution of group A is slightly right skewed, well, Group B is roughly symmetric. Okay? I joined those two into one sentence to describe the distributions. Or we can use comparison words like Group A typically scores higher than Group B. Or the mean of Group A's distribution is greater than the mean of Group B. Or Group B shows more variability than Group A, as seen, and then you can say like as seen in larger IQR, okay? Or, comment on why Group B shows more variability. There's an outlier in Group A that Group B does not have, right? So I'm using these words to compare them. Or in this example, like I first had, if I don't necessarily have a good way to compare them, I tie them together in a sentence, okay, to bring them together to join them in my comparison, okay? Okay, so here's what you should not do in our example, and here's what you should do. What you should not do is say the shape of the AP student homework time is left skewed with an outlier, and the shape of non-AP student homework time is left skewed with no outliers, okay? Don't do that. That's just stating facts, two separate distributions. What you should do is say something like both distributions appeared left skewed, while AP student homework group appears to have a low visual outlier, the non-AP homework group does not. Okay? And I know it's a subtle difference, but it's an important one in AP statistics. When we go into inference and we try to draw conclusions from one variable data or two variable data, we want to make sure that we have these comparison descriptions down, okay? We want to make sure that we're able to compare distributions correctly. So be specific with me, okay? Here's another thing. The mean amount of time AP students spend on homework is 88.905 minutes. The mean amount of time non-AP students spend on homework is 47.3 minutes. Okay? Again, you're stating two separate facts, but you're not really comparing them at all. You're using context, which is important. You want to make sure you have context in all of these descriptions. But when you're asked to compare, you want to actually compare them. So here's what you should do instead. The mean amount of time AP students spend on homework is this many minutes, which is higher than the mean amount of time non-AP students spend on homework, which is this many minutes, okay? You don't want to say, okay, this mean is higher than this mean. You want to include, notice how this includes so much context to the problem, okay? Context to the problem with the actual words between the two groups, what they measure, the units on them, and then using those comparison words. You want to make sure that you do that when you're asked to compare distributions. Okay. And believe it or not, that brings us to the end of our notes for today. I thank you guys so much for following along. If you have enjoyed this video, please hit the like button and subscribe to my YouTube channel for more great AP statistics content. Until then, I wish you endless statistical success, and I will see you in the next video.